Imagine standing right there at the shoreline. You feel that immense rhythmic power of the ocean. It's captivating, almost hypnotic. But for civil engineers, for you, this power isn't just a spectacle. It's a fundamental force you absolutely must understand, predict, and, well, engineer with. How do we build structures sturdy enough to stand against that relentless crash of waves? How do we manage beaches that are constantly being reshaped by forces that are, well, unseen yet incredibly powerful? These are colossal challenges, and frankly, they're just absolutely fascinating. Today, we're taking a deep dive into the foundational and truly captivating world of coastal hydraulics. Our mission, and this is really tailor-made for you, the aspiring civil engineer, is to equip you with the essential theories and practical parameters you'll need, things to help estimate hydraulic factors related to these wave-induced processes. Think of this as maybe your shortcut to understanding the ocean's language, but from an engineering perspective. So what's our roadmap for this exploration? Well, we'll start by dissecting the very basics of waves, understanding how they transform as they journey from the open ocean right up to your shoreline. Then we'll plunge into the, I guess you could say, mathematical elegance of linear wave theory. We'll unravel its key equations and figure out what they truly tell us about wave behavior. We'll also explore the powerful, albeit slower, dynamics of currents and the rhythmic mystery of tides. Before connecting all these forces to the constant reshaping of our coastlines through coastal sediment transport, get ready for an engaging journey. We hope it makes these complex concepts crystal clear, incredibly relevant, and, dare I say, pretty exciting for your future career. All right, let's kick things off by defining our playing field. What is coastal hydraulics exactly, and why does it demand its own specialized focus? I mean, it seems like water is water, right?
That's a great question, and it really gets to the core distinction. Many of us are familiar with river hydraulics, where you're primarily dealing with hydrostatic forces. That's the pressure of water at rest, and drag forces, which is the resistance a fluid exerts on a moving object. These are relatively straightforward, typically acting in a largely predictable, unidirectional flow. Think of a steady river pushing against, say, a bridge pier.
Right, like water filling a reservoir or maybe a boat moving steadily downstream. It's a pretty linear system, generally speaking. Gravity just pulling water downhill.
Exactly. But in the sea, the picture becomes far more complex, much more dynamic, and frankly, far more demanding for an engineer. While we still have hydrostatic and drag forces, you're now adding incredibly powerful wave-induced dynamic forces. These aren't static forces. They fluctuate rapidly, exerting immense oscillating pressures. On top of that, you have constantly varying water levels because of tides and storm surges, sometimes changing by meters in just a matter of hours. This combination of highly dynamic, oscillating vices and fluctuating water levels, it demands a completely specialized understanding. It's a realm utterly distinct from river environments.
Okay, so if I'm understanding correctly, it sounds like the core objective of coastal hydraulics is essentially about understanding and predicting how water moves and interacts with the land in these incredibly dynamic coastal environments, everything from the deep ocean all the way to the shallowest beach. It's truly a holistic view.
Precisely. It's about being able to characterize, quantify, and ultimately predict these interactions with enough accuracy to design resilient structures and manage our coastlines effectively. This field builds on foundational knowledge, often drawing from classic texts like Basic Coastal Engineering by R.M. Sorensen and Waterway Mechanics for Engineers and Scientists by Dean and Dalrymple. These aren't just old books. They form the very bedrock of the discipline, providing the theoretical frameworks that engineers still rely heavily on today.
And why does this deep dive specifically matter to you, our listener, the aspiring civil engineer? This isn't just abstract academic theory we're talking about, is it? We're talking practical applications, right?
Absolutely. The ultimate goal here is intensely practical. It's to enable you to apply these basic theories in a meaningful way. This isn't just about understanding concepts for an exam. It's about being able to estimate crucial hydraulic parameters that directly feed into real-world design decisions. Imagine being tasked with designing a breakwater to protect a vital harbor from storm waves, or implementing measures to halt critical beach erosion that threatens coastal communities, or planning for resilient coastal developments in the face of rising sea levels. Each of these requires a solid quantitative grasp of coastal hydraulics.
That sounds incredibly vital.
This knowledge translates directly into tangible projects.
So by the end of this deep dive, you'll be better equipped to tackle those real-world coastal engineering challenges with a solid theoretical grounding, rather than just relying on, guesswork or rules of thumb. You'll have the confidence to make informed decisions.
That's the key. You'll have the analytical tools to approach these complex problems systematically. Yes.
Excellent. Now, to give you a clear roadmap of what we'll explore today, let's quickly recap the journey ahead. We'll meticulously unpack waves and wave transformation, understanding their incredible journey from the open ocean to the shoreline and how their characteristics shift along the way. Then we'll dive into linear wave theory. This is where the equations come alive to describe wave behavior with remarkable precision. It's really the mathematical backbone of it all. After that, we'll touch upon currents and tides, those slower but equally powerful drivers of coastal change. And finally, we'll connect all these forces to coastal sediment transport, explaining how beaches are literally built, eroded, and constantly shifting, hopefully providing you with a holistic understanding of our dynamic coastlines. All right, let's zoom in on the most visible and perhaps most captivating aspect of the ocean, the waves. We see them, we feel them crashing, but what's actually happening beneath that mesmerizing surface? In this section, we'll break down the anatomy of a wave, explore its unique motion, and then trace its incredible journey and transformations as it approaches the shore. First, let's talk about the anatomy of a wave, starting with its most obvious characteristic, wave height. What defines that for us, simply?
Wave height, usually denoted as h, is the most fundamental visual measure. Simply put, it's the vertical distance from the crest, that's the highest point of the wave, down to the trough, its lowest point. It's the visual measure of a wave's magnitude, what we typically observe when we look at the ocean's surface.
Simple enough. But then there are different types of wave motion that students might learn about in physics, right? We have transverse waves like a ripple on a string where the motion of the medium is perpendicular to the direction the wave travels. And then longitudinal waves like sound waves where the motion is parallel to the propagation direction.
Those are good foundational examples, yes. But here's where it gets really interesting and unique for water waves. They are actually a fascinating combination of both longitudinal and transverse motions. Individual water particles don't just move straight up and down, or simply back and forth, like in those simpler examples. As a wave passes, they actually move in distinct orbital paths. Picture a tiny piece of seaweed on the surface. It doesn't just go straight up and down. It actually describes a circle as the wave passes. And beneath the surface, these orbits become progressively flatter, more elliptical, eventually becoming purely horizontal right at the seabed in very shallow water.
Wow, that explains so much. So it's not just a simple push and pull, it's this whole intricate dance. And crucially, this isn't just a fascinating observation, is it? It's the hidden engine driving how waves transfer energy and sculpt our coastlines.
Exactly. Understanding these particle orbits is absolutely key to predicting everything from sediment movement to the precise forces on submerged structures like pipelines or foundations.
Couldn't have said it better. And these waves, they're not static entities, as you mentioned. They're constantly changing, right? That brings us to the crucial concept of wave transformation.
Indeed. Waves are incredibly dynamic. As they travel across varying water depths and encounter obstacles, they're constantly changing. This journey to the shore is anything but straightforward. It's a continuous process of evolution.
And for you, as a civil engineer, understanding how waves transform is of paramount importance. This dictates everything, really, from the stability of a harbor or coastal breakwater to the safety of a beach for recreation, even the design considerations for sensitive coastal infrastructure.
It's literally the difference between a structure standing strong or, well, failing under stress.
Yeah,
You have to get it right.
absolutely. So let's delve into the key processes of this transformation, what we might call the life cycle of a wave as it approaches the shore.
Okay, our first key process is one, wave shoaling. This is what happens as waves move from deep water into progressively shallower areas.
Mhm.
They begin to feel the seabed, right? And this interaction fundamentally alters their characteristics. You'll observe several dramatic changes. The wavelength, L, decreases significantly. The wave height, H, initially might decrease slightly due to energy spreading out, but then it rapidly increases as the wave compresses vertically. And the wave speed, or celerity C, changes significantly as well. It slows down.
So they slow down, get shorter wavelength-wise, and then dramatically taller, almost like they're gathering all their energy for the grand finale. And that grand finale is, of course, too, wave breaking.
Yes, the dramatic climax of shoaling. This is where the wave becomes too steep and unstable, eventually collapsing under its own weight. This is the point where most of a wave's immense energy is dissipated, often quite violently. We categorize breaking waves often by their appearance and the slope of the beach they're breaking on. A spilling breaker occurs on a mild slope. It's characterized by its foamy crest that gently spills down the face of the wave, dissipating energy gradually over a wider area. A plunging breaker, on the other hand, happens on a steeper slope. Here, the crest curls right over and falls dramatically, forming a distinct air pocket and releasing a huge burst of energy in a concentrated zone. The type of breaking wave tells us a lot about the energy dissipation and the potential for impact.
Then we also have 3, wave reflection. What happens when waves encounter something steep, like a vertical seawall or maybe a natural cliff face? They don't just disappear, do they?
No, they bounce back, exactly. And this isn't just a simple bounce. Reflection can lead to very complex wave patterns, often increasing localized forces right near the structure. Imagine waves crashing against a seawall, then reflecting back out into the incoming waves. You can get this chaotic interference pattern, sometimes called standing waves or clapotis. This can significantly increase the erosion potential at the base of these structures and generate powerful, unexpected forces. It's a critical consideration for engineers designing any rigid coastal defense.
Moving beyond reflection, let's consider 4, wave diffraction, the fascinating way waves can sort of bend around obstacles. This happens when waves bend and spread out as they pass an obstacle or an opening, like a breakwater tip or a gap in a reef.
Diffraction is crucial because it allows wave energy to penetrate into areas that might otherwise seem completely sheltered. For example, behind a protective breakwater, you still get some wave activity reaching the calm area due to diffraction. This is vital for designing safe harbors and marinas, where you need to precisely predict how much wave energy will actually reach the sheltered side of a protective structure to ensure safe mooring and navigation. You can't just assume it's perfectly calm behind the barrier.
And finally, we encounter 5, wave refraction. I like to think of this as the bending of the wave crests as they approach a shoreline at an angle, especially when the depth contours aren't parallel to the incoming wave crests. It's almost like the wave is being distorted or turned.
That's a very good analogy. The mechanism is quite elegant, really. Different parts of the same wave crest will travel at different speeds depending on the water depth they're currently in. The part of the wave in shallower water slows down more quickly than the part still in deeper water. This differential slowing causes the crest line to turn, often aligning it more parallel to the underwater depth contours, and thus often more parallel to the shoreline itself. It's a bit like a marching band, changing direction smoothly as different sections encounter shallower mud or deeper water at different times. This is vital, because refraction either concentrates or disperses wave energy along the coastline, affecting where erosion or deposition will be most intense.
All right, now we're diving into what many consider the very heart of coastal hydraulics, linear wave theory. This is where the mathematical elegance truly meets the raw power of the ocean, giving us the tools to actually quantify everything we just discussed. In this next section, we'll introduce the core assumptions, define the crucial parameters, and then derive the fundamental equations that unlock our understanding of wave behavior.
This fundamental theory, it goes by a few names. Small amplitude wave theory, or sometimes Airy wave theory, honoring George Biddle Airy, who published its correct form back in the 19th century. It's a cornerstone for good reason, providing the basis for many, many modern coastal engineering calculations.
And what's the core assumption that makes this theory so powerful, yet also gives it its linear name? What simplification makes it, well, solvable?
It's based on the key assumption that the wave amplitude is small compared to both the wavelength and the water depth. So relatively small waves compared to the environment they're in. This seemingly simple assumption allows for a linearization of the governing fluid dynamics equations, making them analytically solvable, which is a huge advantage. Despite these simplifications, it provides incredibly useful first approximations for a vast array of coastal engineering problems, from calculating wave forces on piles to understanding basic shoaling patterns.
So why is it so crucial then? Even with its simplifications, why do we rely on it so heavily, especially as a starting point for analysis?
Because it offers the most accessible and widely used framework for understanding the basic kinematics, that's the motion and dynamics, with forces of waves. It's our essential starting point for almost any wave-related calculation. It gives us a robust foundation before we might need to consider more complex, nonlinear theories, which are usually required when accuracy needs are higher or when dealing with more extreme wave conditions like breaking waves.
Okay. To truly speak the language of waves and apply this theory, we need to understand the key parameters and their definitions. Let's lay out these fundamental building blocks. First, we have wave period T.
That's simply the time it takes for two successive crests, or troughs, to pass a fixed point. Think of it as how often a wave arrives at a certain location, measured in seconds.
Then there's wavelength, L, which is the horizontal distance between those two successive crests, measured in meters.
And from those two, we get wave speed, C, or celerity, which is the speed at which an individual wave crest propagates across the water surface. It's defined simply as distance over time. C equals LT. The term celerity, derived from Latin celeritas, meaning swiftness, perfectly captures this speed of wave propagation. What's fascinating here is how these seemingly simple ratios define the very essence of how a wave moves.
Okay, let's unpack this a bit more. We also have wave number k, which is related to wavelength by k equals 2L. It's essentially a measure of spatial frequency. Think of it as how many waves fit into a given distance in radians per meter. And then angular frequency related to wave period by O is 2T. This is a measure of temporal frequency, how quickly the wave oscillates at a given point, in radians per second. These symbols T, L, C, K are the fundamental mathematical building blocks we'll use to describe and predict wave behavior.
Indeed. Now, to truly understand how these parameters fit together mathematically, we turn to the governing equations and boundary conditions. These are the fundamental physical rules that define the behavior of these idealized waves. We start by assuming irrotational motion of an incompressible fluid.
So incompressible fluid means the water density remains constant, which is a pretty good assumption for ocean water in most cases. And irrotational motion means no swirling fluid particles, no significant turbulence or vortices within the flow itself. That simplifies things quite a bit, right?
Precisely. For such an ideal fluid, we can introduce a powerful mathematical tool called the velocity potential. This is a scalar function, meaning it just has magnitude at each point. Its spatial derivatives, how it changes with x and z, give us the components of the fluid velocity. It essentially simplifies the description of the fluid flow, allowing us to derive velocities from its derivatives rather than dealing with velocity vectors directly. The foundation of our analysis is the continuity equation, which fundamentally represents the conservation of mass within the fluid. You might see it written as nabla.u equals 0. For irrotational flow, this beautifully simplifies to the Laplace equation in terms of the velocity potential. Double squared phi equals 0, or mathematically 2 furs RS generator 7 path plus c unit. This famous partial differential equation must be satisfied by the velocity potential throughout the entire fluid domain.
Okay, and then to make it a solvable problem for our specific scenario waves in a water basin of a certain depth, we need to apply some essential boundary conditions, right? These are the critical constraints that define the physical environment where the wave actually exists.
Absolutely. These are non-negotiable physical constraints we have. The lateral boundary condition. We generally assume waves are periodic in both space, x direction, and time t, meaning they repeat their pattern predictably. The bottom boundary condition. The seabed is solid and stationary. There's no flow through it. So the vertical velocity component v's must be 0 at the bottom, which we usually define as z of bd, where d is the local water depth measured positive downwards from the still water level. The dynamic free surface boundary condition. This states that the pressure on the free surface, the interface between water and air, is uniform along the wave, essentially equal to constant atmospheric pressure. So pressure is constant whether you're at a crest or a trough right at the surface. And finally, the kinematic free surface boundary condition. This ensures that there is no flow across the free surface. Water particles initially at the surface remain at the surface as the wave passes. They don't magically leave the water or suddenly get submerged below it. They follow the surface.
By applying all those constraints to the Laplace equation, we can find a specific mathematical solution for the velocity potential. And here's where it gets really interesting. The elegance of the solution allows us to describe the complex motion of water particles using just those few key parameters we defined. The equation for the velocity potential in a progressive wave looks like this. FTOS KD plus Z 2KX. So let's quickly break down those variables again for our listeners. G is acceleration due to gravity. A is the wave amplitude, which is half the wave height, h2. A is the angular frequency. K is the wave number. D is the water depth. Z is the vertical position, usually measured positive upwards from the still water level, so Z at night at the seabed. X is the horizontal position along the wave's direction. And tit is time.
Exactly.
Yeah.
And building on that velocity potential, by using the free surface boundary condition and the linearized Bernoulli equation, we can then derive the equation for the free surface oscillation. This tells us precisely what we see on the surface, the actual wave profile moving up and down. For progressive waves, the surface elevation, that's the vertical displacement from the still water level, is beautifully described by a simple cosine function. E ellipse a coscote. The simple cosine function elegantly describes the rise and fall, the crests and troughs, of a wave as it propagates in space and time. It directly connects our more abstract potential function to the observable world, the wave shape we actually see.
And now for perhaps one of the most important relationships derived from linear wave theory, the dispersion equation. This is what truly unveils how wave speed depends crucially on both water depth and wave period. This is the master key, really, to understanding wave behavior across different conditions.
This is indeed the master equation, you could say. OQ equal GK. KKD. This is called the dispersion equation, and it's the absolute key to understanding why waves behave differently in various water depths. It explicitly links angular frequency, gravity g, wave number k, and water depth d. What this equation fundamentally shows is a phenomenon called frequency dispersion. This means that the wave celerity c, which equals uk, is dependent on the wave period or wavelength and the water depth. So waves at different periods will travel at different speeds in a given depth.
Okay, so the dispersion equation is our master key because it unveils why waves of different periods, say short, choppy wind waves versus long, smooth swell travel at vastly different speeds in the ocean, especially in deeper water. This frequency dispersion is absolutely fundamental to how waves evolve, how they spread out from a storm source, and what kind of energy they ultimately deliver to your coastline. It's like different notes in a musical chord traveling at different speeds through the air.
That's a perfect analogy. And we can indeed manipulate this equation by substituting rho 2T and KKD2 Pel back into the dispersion equation and doing some algebraic rearrangement. We can express celerity, CLT, in different forms. This leads to some crucial, widely used approximations for different depth regimes. First, for deep water waves, or short waves. This condition typically occurs when the relative depth DL is greater than about 12 or 0.5. In this regime, the hyperbolic tangent term, DDKD, approaches 1. It simplifies things nicely. The celerity in deep water, let's call it C, becomes CALG up CT, and the deep water wavelength, LO, becomes LO GT222. The key insight here is profound. Deep water wave celerity depends only on the wave period, T, not the water depth, D. Longer period waves travel faster. This is why swell waves, which have traveled far from their generation area and sorted themselves out by period, travel faster than locally generated wind waves. Then we have the opposite extreme, shallow water waves, or long waves. This occurs when the relative depth DL is very small, typically less than about 125 or 0.04. Here, tan KD approximates to just A itself.
The celerity in shallow water then simplifies to C at the wavelength LZLAG. What's crucial here is that shallow water wave celerity depends only on the water depth, D, and not the wave period, T. All waves, regardless of their period, travel at the same speed in the same shallow depth. Think of tsunamis or even tides. Even in the deep ocean, due to their extremely long wavelengths, they behave as shallow water waves, and their speed is dictated primarily by ocean depth. And for anything in between these two extremes, for 125 DL12, we're in the transition zone. Here, neither simplification is accurate, and the full, more complex dispersion equation, TOPLTA-KKD, must be used for accurate calculations.
This is truly powerful stuff for an engineer. And we even have real-world data that applies these concepts directly. Our source provides, for example, a wave record off Colombo port table. This contains actual recorded wave parameters like H's, which is the significant wave height, often defined as the average height of the highest one-third of waves in a record. T-pay, the peak period, the wave period associated with the most energy in the wave spectrum, and T, the zero crossing period, the average time between successive upward crossings of the still water level. This kind of data is precisely what civil engineers use out in the field to characterize the wave climate at a site and then apply these theories in practice. So what does this all mean for a civil engineer trying to design, say, a breakwater or a pier off the coast of Colombo using this data?
That's a very practical question. It means you take these real-world measurements, like H's and TP from the table, which represent the actual conditions. You use these as inputs into the theoretical framework we've just discussed, the dispersion equation, the shoaling calculations, etc. This allows you to then predict design wave heights at different depths near your structure, estimate the forces those waves will exert, understand potential sediment movement patterns, and so on. It's the critical bridge between the theoretical insights from linear wave theory and the practical realities of engineering design in a specific location.
Let's move on then to particle velocity. Under waves, understanding where the water itself actually moves, not just the waveform propagating across the surface.
Okay. By taking partial derivatives of that velocity potential we found earlier, specifically with respect to x horizontal direction and z vertical direction, we can directly derive the horizontal and vertical vz components of the water particle velocity at any point within the water column and at any time t. These equations tell us the instantaneous speed and direction of individual water particles as the wave passes. The equations look like this: v plus kd plus v plus kd z plus kd plus kd plus f. The cosh kd plus v and cg plus z terms are crucial here. They contain the vertical coordinate z and dictate how the velocity magnitudes change with depth. In deep water, for instance, these hyperbolic functions cause the particle motion to decay rapidly as you go deeper, which is why a submarine at depth barely feels surface waves. At the seabed, at z EDD, their vertical velocities correctly become zero, as we'd expect since there's no flow through the solid bottom. That was our boundary condition.
The horizontal velocity Vx simplifies, and in very shallow water, it becomes almost uniform with depth from surface to bottom.
This horizontal velocity right at the seabed, let's call it VB, is particularly important, isn't it? Especially when we think about what physically moves sediment around on the seafloor and causes erosion or accretion.
Absolutely critical. The horizontal velocity at the seabed, CAPLD, is the key driver for understanding sediment transport dynamics initiated by waves. We can express its maximum value during a wave cycle as VB max, GHT, 2L, 1 cosh, KDD. Here H is the wave height, H2A. Now for erosion or sediment movement to actually begin, this seabed velocity, VB, must exceed a certain critical threshold velocity, often called VC. If V remains less than VC, the bed material will stay put, it will be stable. VC itself isn't a fixed constant value. It depends on the specific properties of the bed material, things like the size, density, shape, and packing of the sand or gravel grains. Understanding this threshold velocity concept is fundamental for predicting whether a beach will erode or accrete under given wave conditions, and therefore for designing effective coastal protection measures. It's really the battleground where the wave's energy meets the resistance of the seabed.
So we've talked about velocity, the speed of the particles. Now let's talk about particle displacement under waves, the actual orbital dance we mentioned earlier. What path do these individual water particles trace out as a wave goes by?
Imagine a specific water particle initially at some mean or average position, x, u, or z. As a wave passes, its actual position changes over time to x, u, or t. The displacement from its mean position is what we denote by xt, horizontal displacement, and zt, vertical displacement. We can find these displacements by integrating the velocity components vd and v with respect to time, making the approximation valid for small amplitude waves, that the velocity at the particle's mean position is close enough to its actual velocity. Doing this integration yields CTCTD seen.
When you look at these equations for xt and zt, what emerges mathematically is a beautiful visual. Water particles don't just bob straight up and down, they actually trace out an elliptical path. These equations are the parametric representation of an ellipse. If you plotted x versus z over one wave period, you'd draw an ellipse. It confirms that orbital motion we introduced conceptually right at the beginning.
Exactly. And a key characteristic derived from these equations is that the horizontal extent of the ellipse, related to the horizontal semi-axis AX, is always greater than or equal to the vertical extent, related to the vertical semi-axis AZ. The orbits are generally flattened ellipses, especially near the surface. These ellipses become progressively flatter, more horizontal motion, less vertical, as you go deeper towards the seabed. In deep water, they become circles near the surface. This orbital motion is absolutely crucial for understanding how waves transfer energy, transport sediment, especially near the bed, and apply forces to submerged structures. It's far more complex than just pushing water forward in a straight line.
And finally, for this foundational section on linear theory, let's uncover the pressure field. Under progressive waves, the hidden, fluctuating force beneath the surface that structures need to be designed to withstand.
Okay, we start with the generalized Bernoulli equation, which relates pressure, velocity, and elevation in a fluid flow. But we use the version for unsteady flow. We then linearize it by dropping the velocity squared terms, which are small for small amplitude waves consistent with our theory. The pressure P at any point under a wave, relative to atmospheric pressure, is then given by BP, work as the fluid density. This equation reveals two distinct components of pressure that are critical for engineers to understand. The first term is the familiar hydrostatic pressure, UX, or UX as Z, if Z is positive upwards. This component is always present, regardless of waves, and it increases linearly with depth below the still water level, SWL. It's just the weight of the water above. The second term is the wave-induced hydrodynamic pressure. This dynamic component exists only when waves are present. It comes directly from the time-varying part of the velocity potential. This wave-induced pressure varies sinusoidally with the wave's passage. At a fixed depth, Z, it reaches a maximum positive value directly under a wave crest, adding to the hydrostatic pressure, and a maximum negative value, a suction relative to hydrostatic, under a wave trough. This oscillating pressure can exert significant fatigue forces on structures.
And this leads us to a critical engineering parameter, the pressure response function, Kp, which simplifies this analysis for practical use, relating the pressure fluctuation to the surface elevation.
Exactly. The pressure response function is defined as Kp apodynamic, where P dynamic is the amplitude of the dynamic pressure fluctuation and Kp is the surface elevation. Using our theory, this simplifies beautifully to
Kp equals cosh Kp plus z Kab. The pressure response function Kp is incredibly useful because it tells us the ratio between the amplitude of the dynamic pressure head fluctuation at depth z and the water surface elevation amplitude a, since Bmax is a. It essentially tells you how much of the surface wave's pressure signal penetrates down to a certain depth. This is vital for designing submerged structures like pipelines, tunnels, foundations for offshore platforms, or even the stability of breakwater armor units. Understanding how wave-induced pressure varies with depth is paramount to ensure their stability and longevity. Without Kp, you'd be designing blind to a major fluctuating force component.
Okay, we've established the fundamentals of linear wave theory, the equations, and the basic concepts. Now, let's dive deeper into some of the most critical wave transformations we introduced earlier, specifically shoaling and refraction, but this time with a more quantitative lens, using the mathematics we just laid out. We'll start with wave energy content and transfer. Because, as we said, waves aren't just motion, they're carriers of immense energy, and understanding how that energy is quantified and how it moves is crucial for any civil engineer designing for the coast.
Absolutely. The energy content, E, is defined as the total energy that's potential plus kinetic stored within a wave, averaged over one wavelength, per unit horizontal surface area. For a linear wave, this average energy density is given by a remarkably simple formula. E equals 18 AgH, or equivalently E equaling 12, Senshis 2a. This equation is incredibly important because it shows that wave energy is proportional to the square of the wave height, h. This means even a small increase in wave height, say doubling it, leads to a fourfold increase in the energy content and thus its potential for damage. This quadratic relationship is a critical insight for engineers assessing risk. It's the fuel driving all the processes we're discussing.
So that's how much energy a wave contains per unit area. But then there's energy transfer, often called energy flux, or simply wave power. This describes the rate at which that wave energy is transferred forward, moving through a vertical plane of unit width that's perpendicular to the wave propagation direction. This is a measure of how quickly that energy is actually moving towards the shore or a structure.
Correct. The mechanism involves water particles moving back and forth, carrying their kinetic energy across this imaginary plane. They also have potential energy due to their position. Additionally, the pressure exerted by the wave does work on the water particles as they move across the plane. When we average this energy flux over a complete wave period, it simplifies to a very useful equation for the average wave power per unit width, often denoted P, PPE, EG, equals E, N, C. Where E is the average energy density we just defined, C is the phase velocity, the speed of an individual crest, and CG is what we call the group velocity. The factor N relates the two, CG equal NC.
Group velocity. This is a fascinating concept, sometimes counterintuitive. The individual waves, the crests, seem to move at one speed, c, but the energy of a group or packet of waves actually moves at a different speed, cg. Why the distinction? And why is cg the important one for energy transfer?
It's exactly. Group velocity, CG equals NC, is the speed at which the wave energy actually propagates forward. It's typically the speed at which a wave group, or a packet of several waves, travels across the ocean surface. The factor N is the ratio of group velocity to phase velocity. N equals CGC. Its value depends on the relative depth, dl. In deep water, dl12, N is approximately 12. This means the wave group travels at half the speed of the individual wave crests within it. You can often see this on the ocean. Individual waves appear to form at the back of a group, travel through the group faster than the group itself, and then disappear at the front. The group as a whole moves slower. In shallow water, dl125, N approaches 1. Here the group and phase velocities become nearly identical. The wave shape and the energy travel together. This subtle but profoundly important distinction is crucial for engineers, because ZG tells us the rate at which destructive wave energy is actually delivered to a structure or a coastline. The power P depends on CG, not C.
Okay, now let's connect this energy concept back to wave shoaling. But this time, let's look at the quantitative analysis. As we discussed earlier, waves undergo profound changes as they enter shallower water, particularly in height.
A key assumption, and often a very good one away from breaking in shoaling calculations, is the principle of energy conservation between wave rays or orthogonals, lines perpendicular to wave crests. We assume that, barring energy loss to friction or breaking, the wave power P remains constant as the wave travels from deep to shallow water between two adjacent orthogonals. So the energy flux must remain constant. P. Using our formula for P, this means ECG or EMENZ, where the subscript 0 denotes deep water conditions.
This is the fundamental principle for predicting how wave height changes due to depth changes alone.
And from this energy conservation principle, we can derive the Scholing coefficient Ks, which directly quantifies how the wave height h changes relative to the deep water wave height h during shoaling.
That's right. Since E is proportional to HEG, the energy conservation equation becomes HEH equals in HEH. Rearranging this to solve for the ratio HH gives us the Scholing coefficient, KGS HH HACEG. This equation is vital because it tells us, for a given deep water wave, how tall the wave H will be at any shallower depth before it breaks, assuming only shoaling is happening. As we noted, as a wave approaches the coast, K typically decreases slightly at first, as CG might initially increase relative to C in intermediate depths. But then it increases rapidly as the wave enters very shallow water, where CG decreases significantly, eventually leading to the depth-controlled wave breaking.
To really solidify this, let's walk through that example calculation again, applying this formula. This is the kind of problem you'd encounter in a real coastal engineering scenario. Remember, a wave with period t each 8 seconds travels from deep water to a shallow beach. Its height is 1.5 meters at 10 meters depth. What is its height at 8 meters depth? This isn't just theory, it's the kind of calculation for understanding hazards or design.
Exactly. Let's apply the Scholing coefficient logics step by step. First, find the deep water characteristics. For TEHs, we found LO 100 meters in deep water and L. Let C euro L 100 meters. So C euro and C euro equals in find C euro. 2. Next, determine conditions at D equals 10 meters. Relative depths DL arrow equals 100 and L.1. From wave tables or by solving the dispersion equation for this DL arrow and T8s, we find the local wavelength L arrow, celerity C, and the factor N. Let's say the tables give us C euro and N rho. Then we find CG10 L or C euro. 3. Then determine conditions at DL's 8 meters. Relative depth DL euro is at date all 100 intervals for this depth. Then calculate CD air 4. Now apply the Scholing relationship. We know H euro, H we can use this to relate the heights at 10 meters and 8 meters. AC to euro, dividing these gives H euro using the values derived from wave tables, as in the source example, which effectively calculated CG, H, and CD euros directly. H is 0.9327, 0.9768, and L 0.9883. Note, these numbers represent the ratio CG-CGO.
5. Finally, calculate H at 8 meters. Since H is 1.5 meters, then H equal H.9883 equals 1.9883 at 1.48 meters. This example highlights the power of linear wave theory and the Scholing coefficient in predicting how wave heights change purely due to depth variations. You see the height slightly decreased, moving from 10 meters and 8 meters in this specific case.
That's incredibly helpful. It shows how these calculations directly translate theory into practical predictions. Now let's move to wave refraction, again looking at the quantitative analysis. As we reviewed earlier, this is the bending of wave crests as they move into shallower water at an angle to the depth contours.
Indeed. Just like light rays bending when they pass from air to water, waves refract as they move through varying water depths because their speed changes with depth. And for waves, the governing principle is Snell's law, adapted for water waves. It describes the relationship between the wave direction, represented by the angle of wave orthogonal relative to the depth contour normal, and the wave celerity C at different depths. Since here, rearranging, sin, A. Here, on and os are the angles of the wave orthogonals at locations 1 and 2 with depth sus. And C are the corresponding wave celerities at those depths, found using the dispersion equation. This law allows us to predict precisely how a wave's direction will change as it encounters changing bathymetry. Now, for the height change due to refraction, again, similar to shoaling, we assume energy conservation, but this time between two adjacent wave orthogonals. As the wave refracts, the distance b between these orthogonals can change. If they converge, b decreases, energy is concentrated, and wave height increases. If they diverge, b increases, energy spreads out, and wave height decreases. The energy conservation equation between orthogonals is POBOI, POB, which means EOD1 BOI. Geometry tells us how the orthogonal spacing b relates to the wave angle BOA, Ikiko Oros, for a zone cut.
And just like with shoaling, we can define a coefficient to quantify the change in wave height due solely to this bending effect, the convergence or divergence of orthogonals. That's the refraction coefficient, Kr.
Correct. Substituting E proportional to H dr and the relationship for B into the energy conservation equation gives H2 at key do 1, key d year. If we only consider the effect of changing orthogonal spacing, ignoring the change in CG for a moment, which is handled by shoaling, we can define the refraction coefficient as Kr equals H ties. Now, in most real-world scenarios, both shoaling,
due to depth change and refraction due to angle change and depth change affecting speed occur simultaneously. So to get the total change in wave height from deep water HD or to a point H at depth D with angle R, we need to combine both effects. The total wave height is found by multiplying the deep water wave height H by both the shoaling coefficient Ks and the refraction coefficient Kr, H or Ks, Kr, where Ks, Kr, annual. Note, often R in deep water is the initial angle, and I is found using Snell's law iteratively. This comprehensive approach is what engineers must use for accurate nearshore wave height prediction.
Let's run that second example calculation again, navigating complex depths using this combined approach. Remember, a slope with straight parallel depth contours transitions between 12 meters and 6 meters depth. Incident wave direction H up, angle of orthogonal to contour normal, is 30 degrees at 12 meters depth. Wave period T equals 8. Wave height H arrow at 12 meters depth is 3 meters. Calculate the wave height H arrows at 6 meters depth.
Okay, this is a classic problem requiring both Snell's law for the angle change and the combined energy conservation for the height change. Here's the step-by-step thinking. 1. Deep water characteristics. Again, for T's HS, L are 100 meters. We'd also need the deep water angle IR. It's starting from deep water, but here we start at 12 meters. 2. Conditions at DL0, HL0, 0.12. HL is 30 degrees. HL is 3 meters. We need to find C arrow HOS CG1 for 0.12 from tables or calculations. 3. Conditions at D euro 6 meters, HL 0.06. We need to find C euro and thus C euro for DL 0.06. Plum applies Snell's law to find C euro. We calculate C and C using the dispersion relation for the given depths and period. Plug them in with A arrows 30 degrees to find A arrow. The source example calculation yielded I arrow 22.27 degrees. This tells us the wave has bent toward being more parallel to the contours. 5. Calculate the combined shoaling and refraction effect. We need the ratio H arrow. The combined formula derived from H arrow HL arrow relating to intermediate depths is H H arrow, CG1 of B. Substituting BBO, cos gives. Substituting B Ausers of gives. H Ausers gives. We now plug in the calculated values. CG1 from NS arrows at 12 meters, CG grows at 6 meters, which was 30 degrees, and now gyros a 22.27 degrees. Calculate H at 6 meters. Performing the calculation using the values from the tables for CG1 and CGO, or their ratios relative to C, and the angles, the source finds the ratio H arrow allows calculation of H. For H arrows 3 meter, the source calculation gives HE 3.132 meters. So in this case, the wave actually got slightly taller, moving from 12 meters to 6 meter depth, because the combined effect of shoaling, which tends to increase height in shallower water, and refraction, which likely caused convergence here, also increasing height, resulted in a net increase. This detailed calculation demonstrates how engineers must meticulously account for both depth changes and the underwater topography through refraction to accurately predict wave heights. It's fundamental for safe and efficient coastal design.
Finally, for this section on transformations, as waves reach their ultimate limit, they break. So let's briefly revisit wave breaking criteria and understand that crucial point of no return for a wave. This is obviously a critical factor for shoreline protection and design loads.
Absolutely. Most commonly near coasts, we deal with depth-controlled breaking. As wave height H continues to increase during shoaling, and possibly refraction, it eventually reaches a critical limit relative to the local water depth D. The wave becomes too steep to support itself. A widely used approximation, originally suggested by Monk in 1949 based on solitary wave theory, is that a wave breaks when its height HB reaches approximately 0.78 times the local water depth dB at the breaking point, HBU of 0.78 dB. This provides a simple, yet often reasonably accurate rule of thumb for predicting the breaking depth and breaking wave height. More complex criteria exist, often involving wave steepness as well.
And the type of breaker matters too for how it dissipates energy and impacts the coastline and the structures we might build there, right? We mentioned spilling, plunging. Not all breaking waves behave the same way.
It absolutely does matter. The surf similarity parameter, also known as the Iribera number, is a useful dimensionless parameter that helps characterize the type of breaker we can expect. It relates the beach slope to the wave characteristics. It's often calculated using the deep water wave characteristics, where HL is the beach slope angle and HLO are the deep water wave height and wavelength. The value of H tells us about the breaker type. For spilling breakers, H is typically less than about 0.5. These occur on gentle slopes. They are characterized by foam and turbulence spilling down the front face of the wave, dissipating energy gradually over a relatively wide surf zone. For plunging breakers is roughly between 0.5 and 3.3. These happen on steeper slopes. Here, the crest curls over dramatically and plunges down, often trapping an air pocket. These are often considered the most energetic and potentially destructive breakers, releasing energy intensely in a narrow zone. Great for surfing, maybe not so great for structures. And for surging and collapsing breakers, H is greater than about 3.3. These occur on very steep beaches or structures. The wavefront surges up the slope with minimal breaking, or the base of the wave might collapse right at the shoreline. Understanding these breaker types is critical for coastal protection design, estimating sediment transport in the surf zone, and assessing forces on structures. Each type dissipates energy differently and interacts with the coast in a unique way. Engineers use this parameter S to help predict how waves will behave at the shoreline.
So far, we focused heavily on waves, and rightly so, as they are often the dominant energetic force, especially for design. But there are other powerful, sometimes slower, yet incredibly persistent forces at play in coastal environments that civil engineers must also understand and account for. In this final section, we'll briefly revisit wave diffraction, then explore coastal currents, the rhythmic dance of tides, and finally, bring it all together with coastal sediment transport, which is really the engine of long-term shoreline change.
That's right. And just a quick revisit, as you said, to reiterate that wave diffraction is that lateral spreading or transformation of wave energy. It's what allows waves to bend around barriers and spread into what might otherwise seem like calm shadow zones behind breakwaters or islands. It creates complex wave patterns in harbors and lee sides of structures that engineers must predict for effective and safe design. You might build a breakwater to block waves, but diffracted waves will still sneak around the edges, and you need to calculate their height and impact inside the supposedly protected area.
Okay, moving beyond waves then, we have the broader category of currents in the coastal zone. These slower, but often incredibly persistent movements of water also play a huge role in shaping our coastlines, affecting everything from navigation channels to where pollution might end up.
Indeed. And we can categorize these coastal currents broadly by their scale and what drives them. First, you have large-scale oceanic circulations. These are the major global currents, like the Gulf Stream or the Kuroshio Current. They transport vast amounts of water and heat across entire ocean basins. While they mostly affect offshore conditions, their influence can extend to larger-scale coastal water properties and sometimes influence nearshore currents indirectly. Then, critically important in coastal engineering are longshore currents. These are currents that flow parallel to the coastline, typically confined within the surf zone. They are primarily generated by waves approaching the shore at an angle. The oblique wave approach pushes water along the beach. Longshore currents are absolutely critical for understanding beach evolution because they are the primary mechanism for transporting vast quantities of sand along the coastline. This littoral drift leads to erosion in one area and deposition, accretion, in another, constantly reshaping our beaches. Then there are rip currents.
Ah, yes, you've probably seen warning signs about these at the beach. Rip currents are strong, relatively narrow currents that flow rapidly away from the shore, often perpendicular to the beach, through gaps in sandbars or against structures. They're a direct result of wave setup and variations in breaking along the shore, and they pose a significant hazard to swimmers. Understanding their formation and likely locations is key for coastal safety planning.
Absolutely. And finally, we have tidal currents. These are the horizontal water movements caused directly by the rhythmic rise and fall of tides. As the tide comes in, floods, or goes out, ebbs, huge volumes of water move, creating currents. These are particularly important for navigation in harbors and estuaries, for designing mooring systems, and for predicting sediment movement in tidal inlets and channels. They can be very powerful in confined areas.
Speaking of which, let's talk specifically about tide, the rhythmic, predictable breathing of the ocean. What exactly defines tides, and what drives these immense daily or semi-daily cycles of water level change?
Tides are the periodic rise and fall of sea levels. They are primarily caused by the combined gravitational forces exerted by the moon and the sun on the Earth's oceans, coupled with the effects of the Earth's rotation. What's particularly fascinating here is how the alignment of these celestial bodies affects the tide's range. For instance, spring tides occur during the new moon and the full moon phases. This is when the Earth, moon, and sun are roughly aligned. In this alignment, the gravitational forces of the sun and moon act together, reinforcing each other. This results in the most extreme tidal range, the highest high tides and the lowest low tides during the lunar cycle. This means greater potential for coastal inundation at high tide and maximum exposure of the intertidal zone at low tide.
And the opposite of that would be neap tides, right? What happens then when they're not aligned?
Correct. Neap tides occur during the first and last quarter phases of the moon. At these times, the moon and sun are at approximately right angles relative to the Earth. Their gravitational forces act in quadrature, partially canceling each other out from our perspective. This leads to much smaller differences between high and low tides, meaning a smaller or neap tidal range. And as we mentioned, these constantly changing sea levels are what drive the tidal currents, the horizontal movement of water trying to keep up with the changing sea surface slope. Our source material even provides specific local data on sea level change due to tide off Colombo Port. It shows things like the annual maximum and minimum tidal heights recorded over several years, as well as the annual mean sea level variation. This kind of localized tidal data is absolutely crucial for practical engineering applications. Tides directly influence required water depths for navigation, the necessary design height of coastal structures like seawalls or docks, and flood protection levels. You need local data.
This isn't just about these predictable daily or monthly cycles, though, is it? Especially when we factor in the accelerating impacts of climate change and sea level rise. That adds another layer entirely.
It absolutely does. And it raises a critical question. If the predicted global average sea level rise is, say, 0.59 meters over the next 100 years, as indicated in the hazard profile of Sri Lanka referenced in the source, how does this long-term rise interact with these existing natural tidal ranges to impact coastal areas? A higher mean sea level means that what was once considered an extreme high tide, like a king tide or storm surge combination, could become a much more regular occurrence in the future. This kind of data, combining predicted sea level rise with local tidal ranges, helps us to visualize and predict areas that may become permanently or frequently inundated by 2100. It profoundly shifts our engineering perspective from designing for historical conditions to designing for future resilience and coastal adaptation.
And finally, let's bring all these processes, waves, currents, tides, sea level change together, and look at their cumulative effect on coastal sediment transport. This is the constant process reshaping our shorelines, the very essence of beach dynamics and long-term coastal evolution. This is where all those hydrodynamic forces truly manifest themselves visually.
Indeed. The movement of sand, silt, gravel, and other sediment particles along the coast, longshore, and across the coast, on offshore, is a relentless, continuous process. It's driven by the combined action of waves and currents imposing forces on the seabed. There are two primary modes we focus on. First is longshore transport, also widely known as littoral drift. As we discussed, this is the movement of sediment parallel to the coastline, primarily driven by those longshore currents generated by waves breaking at an angle. It results in the gradual shifting and redistribution of entire beaches, eroding sand from updrift areas and depositing it further down the coast in the downdrift direction. This process can lead to significant management problems like chronic erosion threatening infrastructure, beach starvation, or navigation channels filling in with sand, harbor infilling. Understanding and quantifying littoral drift is crucial for designing coastal structures like groins or detached breakwaters, or for planning effective beach nourishment projects. The second mode is on-offshore transport, sometimes called cross-shore drift. This involves the movement of sediment perpendicular to the shoreline, primarily influenced by the action of shoaling and breaking waves, especially during storms versus calmer periods. While waves in deep water cause orbital motion but little net transport, as waves shoal, break, and run up the beach, their shades and the associated water velocities become asymmetric. This asymmetry can create a net movement of sediment either offshore, typically during high-energy storm conditions with steep waves, or onshore, typically during lower-energy swell conditions with flatter waves, helping rebuild the beach.
So it really comes back to those seabed velocities we calculated earlier using linear wave theory, interacting with that critical threshold velocity for sediment movement, VC, that determine if erosion or accretion happens in the cross-shore direction as well.
It's exactly. When the instantaneous wave-induced velocities near the seabed exceed that critical threshold, VC, which depends on the sediment size and density, sediment grains begin to move. The direction of net movement over a wave cycle or a longer period depends on the complex interplay between wave shape asymmetry, gravity acting on the slope, and potentially underlying currents. And importantly, as you mentioned, sediment size matters significantly. Different patterns of movement and transport rates are observed for fine sand versus coarse sand or gravel. Fine sand is more easily suspended and carried further, while coarse sand might just roll or saltate along the bed. This continuous cross-shore and longshore movement is what leads to either an advancement of the shoreline accretion or a retreat erosion. Sometimes these changes happen gradually, other times quite rapidly during major storms. The Calcutta Bay example mentioned in the source, showing beach advancement, accretion, vividly illustrates how these dynamic processes can naturally reshape our coastlines over time. Understanding these sediment transport mechanisms, both longshore and cross-shore, and being able to predict them even approximately is absolutely paramount for sustainable coastal zone management, designing effective beach nourishment strategies, or implementing protective schemes like breakwaters or seawalls that minimize unintended negative impacts on adjacent coastlines. It's the ultimate application of everything we've discussed. Hashtag text, hashtag outro.
And with that, we've navigated the complex, challenging, and truly dynamic world of coastal hydraulics. From the fundamental physics of waves and their intricate transformations like shoaling and refraction to the, well, sometimes complex but elegant mathematics of linear wave theory, we've broken down critical concepts like wave energy, group velocity, particle motions, pressure fields, and the subtle but powerful influences of currents and tides, all culminating in how they drive sediment transport and shape our coastlines. Hopefully, you now have a deeper appreciation for the immense forces at play and, more importantly, the essential theoretical tools and practical parameters that civil engineers use to work with these forces, rather than simply fighting against them as they design for our future coastlines.
It's definitely a field where powerful theory meets dramatic, sometimes destructive, reality every single day. And the stakes for getting the engineering right are often very, very high, involving safety, economics, and environmental protection.
Absolutely. And as we look ahead, thinking about your future careers, here's a provocative thought for you to consider, building on what we've discussed. As civil engineers facing a changing climate, how might the increasing frequency and intensity of extreme weather events, think stronger hurricanes generating larger waves, more intense storm surges riding on higher mean sea levels, how might these challenge the very assumptions and the direct applications of these classical coastal hydraulic theories, like linear wave theory, in our future engineering designs? What new models, what more adaptive strategies, perhaps what new interdisciplinary approaches blending engineering with ecology or social science might we need to develop to ensure truly resilient coastlines for generations to come?
It's a critical and rapidly evolving challenge. It will undoubtedly require ongoing innovation, refinement of these foundational principles, perhaps greater use of complex numerical models, and certainly a willingness to adapt engineering practice to handle conditions potentially outside the range of historical experience. It really pushes the boundaries of what we've discussed today.
A truly exciting and vital area for your future study and work. Thank you so much for joining us on this deep dive into coastal hydraulics. Keep learning, keep questioning, and keep building a better, more resilient future.